Here we have a graph of exponential decay where n refers to the number of radioactive nuclei, right, as a function of time. And so this equation describes our graph. So this would be the number of radioactive nuclei at any time t is equal to n naught, the initial number of radioactive nuclei, e to the negative lambda t. And lambda is equal to the decay constant. So this is just some constant number here. And you could also call this k if you wanted to. You could call it k if you're thinking about the rate constant. So that's just some constant, and then we're going to multiply it by the time here. So let's say we wanted to find what this point right here represents on our graph. Well, that's when time is equal to 0. So let's plug in time is equal to 0 into our equation. So this would be the number of radioactive nuclei when time is equal to 0 is equal to n naught times e to the negative lambda times t, which is 0. So that is equal to, this would be n naught times e to the 0. E to the 0 is 1. So the number of radioactive nuclei at time is equal to 0 is equal to n naught. So this represents n naught, the initial number of radioactive nuclei on our graph. And you could do this for any time t, right? You could just pick a time, let's say that's our time that we wanted, right? And go up to here and find what this value is on the graph. And so at any time t, right, this would represent the number of radioactive nuclei. Let's do it for half-life. So remember, when time is equal to a half-life, right, the number of radioactive nuclei, this would be, let's do 1 half-life, so this would be the initial divided by 2. So half of it remains. So let's look at that on our graph, right? So if we take n naught, we divide that by 2, that's approximately here. So let's say this is n naught over 2. And we go over to here, and we drop down to our time. So this should represent our half-life. That time should represent our half-life. So that's what it looks like graphically. Let's take these numbers. Let's take the half-life and what the number of radioactive nuclei would be, and let's plug it into this equation. All right. So let's go ahead and do that. Let's get some more room. So I'm just going to rewrite that equation here. So we had the number of radioactive nuclei as a function of time is equal to the initial number of radioactive nuclei times e to the negative lambda t. So let's plug in those. So when we're going to talk about the half-life, we're going to plug that in here for the time, and then the number of radioactive nuclei would be n naught divided by 2. So let's plug those in. So we would have n naught divided by 2 is equal to n naught e to the negative lambda times the half-life. All right, well that cancels out the n naughts. All right, so that gives us on the left side 1/2 is equal to e to the negative lambda times the half-life. So next, let's get rid of the e, and we can do that by taking the natural log of both sides, right? So if I take the natural log of 1/2 on the left side, and I take the natural log of e to the negative lambda t 1/2, all right, on the left side, natural log of 1/2 is equal to negative 0.693. So this is just plug it in your calculator. You'll get negative 0.693. And the right, that takes care of this, and all that's equal to just this over here, right? So now we would have, this would be negative lambda t 1/2. And so we don't have to worry about the negative signs, right? So this is just 0.693 is equal to lambda times t 1/2. So we could solve for the half-life, right? So if we solve for t 1/2, so t 1/2 would be equal to 0.693 divided by lambda, divided by the decay constant. And so this is one of those equations, right, that you see for half-life. So what if you wanted to go ahead and solve for lambda, the decay constant, right? So that's obviously really simple. We just do the decay constant is equal to 0.693 divided by the half-life. And so obviously I'm just rearranging this equation here. So you could solve for half-life, or you could solve for the decay constant. You go back and forth between the half-life and the decay constant. So if you know one, you can figure out the other one. All right, so that's thinking about the exponential decay graph. Let's talk about semilog plots next, which is another way of looking at the data. And so let's get some room here. I'm going to rewrite our equation, right? So the number of radioactive nuclei is equal to the initial number times e to the negative lambda t. All right, so let's convert this into a straight line. And so we have to divide by n naught. So we have n divided by n naught. So we divide both sides by n naught, and we get e to the negative lambda t here. All right, now to get rid of this e, once again, we just take the natural log. So we're going to take the natural log of both sides. So natural log of n over n naught is equal to the natural log of e to the negative lambda t. All right, so on the left side, we have a log property. So natural log of n over n naught is equal to natural log of n minus natural log of n naught. And then on the right, this goes away, and we're left with this. So negative lambda t. So we have negative lambda t on the right side here. And if we just rearrange this, so let's just do natural log of n is equal to negative lambda t. So we're going to add ln of n naught to this side. And now we have a very interesting form. If you look at it closely, you'll see this is the same thing as y is equal to mx plus b, which is the equation for a straight line. So y would be equal to natural log of n. M would be equal to negative lambda, so we're talking about t, as being x here, and then natural log of n naught is equal to b. So y is equal to mx plus b, if you remember, equation for, it's the graph of a straight line, where m is the slope, so we could say the slope of this is equal to negative lambda. And remember that this is your vertical intercept, So b is your vertical intercept. So if we graph this, our vertical intercept should be natural log of n naught. So let's go ahead and sketch this out really quickly. So I won't be too concerned with details here, but if we're graphing it, so if you think about this as being your y-axis, I'll just put this in parentheses because that's not really what we're doing, and this being your x-axis, let's look at those again. So for my y, I would be graphing natural log of n. So let me go ahead and use a different color so we can see it here. So natural log of n on the y-axis. On the x-axis here, that would be time. So we have time over here. And we know that the vertical intercept is going to be natural log of n naught. So this vertical intercept here is going to be natural log of n naught. And we could prove that really quickly. We could say when time is equal to 0, so when time is equal to 0, let's plug that in. We'd have natural log of n, which is equal to negative lambda times 0 plus natural log of n naught. So this would go away, and you can see that we would have natural log of n naught would be equal to this point here. So that's our vertical intercept. And we know this is the graph of a straight line, and we're going to have a negative slope here. So if I go ahead and draw this in, it would look something like, just pretend like that's a straight line. I didn't do a very good job, but you can use your imagination there. And the slope of this, so the slope, remember what slope is, that's change in y over change in x, so that would be the change in this axis over the change in this axis. That's equal to, that is equal to negative lambda, we talked about over here. And so if you do a semi-log plot, right, so it's semi-log because we have this this natural log over here versus here, it tells us some information, right? It's just another way to look at the data. You could find the slope of this straight line, right, take the negative of it, and get your decay constant. And then from your decay constant, you could get your half-life. And so once again, sometimes you'll see semi-log plots done as just a different way of looking at the data.